Has this ever happened to you? Why is the center section out? Well, stay tuned and we'll find out on this episode of The Online Physics Teacher. Welcome back to the channel. If this is your first time here, I'm Robin DeMarco, the online physics teacher, and my passion is taking the mystery out of physics and helping to supercharge your science education. For the best information about physics tips and tricks, subscribe to the channel and hit the bell to be notified when I post a new video every Friday. So far, we've looked at simple circuits, either series or parallel. And if you haven't watched those videos yet, take a check up there and check those out. And it might be a good idea right now to actually pause this video and do that, because what we're going to cover today really depends on what was covered in those videos. So let's go back to the example of the holiday lights. Why is it that a section of these lights are out, but the others are still on? We have what is commonly known as a combined circuit, a circuit that has elements that are both connected in series and in parallel. So let's head over to the whiteboard and see if we can get a better idea of what's happening here. Now for this example, we're going to keep things relatively simple. We're going to have a power source going into a parallel circuit. Now, one branch of the circuit has a single light, while the other branch has two lights. And those two lights are connected end to end in a series circuit. This circuit has properties of both a parallel and a series circuit. So for example, if I break the wire on the single light path, the lights in the series will remain on. If I reconnect that, so everything's back on, and now I break the connection between the two lights on that side, both of those lights are going to go out. But we see that the parallel light stays on. So to demonstrate how to analyze this circuit, let's do an example based on the diagram that we already have. We're going to label the lights as R1 as 360 ohms, R2 is 430 ohms, R3 at 125 ohms, and we're going to use a 12-volt battery. We're going to begin by drawing the circuit and labeling everything that we can. Now, of course, at this point, we already have it done because we used it for the example. But now what I want to do is I want to take and spread this circuit out. And if you can imagine grabbing one end of the battery and then pulling it across the string. So I want to have a straight line of this circuit. What we're going to do now is we're going to start at the middle and work our way to the ends. So in this case, in the very center, we see we've got the parallel circuits. But more precisely, on one of those lines, I have the series circuit, or the series resistors, R2 and R3. So I want to get those to an equivalent resistance. So since they're in series, we get that by adding them together. Req, and I'm going to call it Req1, equals R1 plus R2, or 430 ohms plus 125 ohms equals 555 ohms. Okay, redraw the circuit. But this time, instead of having the two R2 and R3 in there, we're going to have just a single resistor, Req1. Now again, we go back to the center. Well, what do I have in the center? I have a parallel circuit this time. So this time we have R1, which is the 360 ohm resistor, and I have Req1, which is a 555 ohm resistor. So what we're going to do now is we're going to use the method we have for finding the equivalent resistance again. Parallel circuit, it's 1 over Req is equal to 1 over R1 plus 1 over R2. Well, in this case, it's going to be the 1 over the total resistance, RT, is equal to 1 over R1 plus 1 over Req1. So we're going to have 1 over 360 ohms plus 1 over 555 ohms is equal to the total 1 over the total resistance, which is equal to 0.0046 per ohm. Now, in order to get RT, I have to take the inverse of that. So we get that RT is equal to 218.4 ohms. And because of significant figures, I only want 3, so I'm going to use 218 ohms. Okay, again, we're going to redraw the circuit. So what happens here now is we have just a single resistor that is currently in place of all the resistors we started with. Now I can look at what I know. I know that the voltage is 12 volts. I know that the resistance, the equivalent resistance in this circuit is 218 ohms. And I want to find the current going through this. So what we're going to do is we're going to apply Ohm's law, Vt equals It times Rt, and we're going to solve for the current. So we're going to get that It, the total current, is equal to the total voltage divided by the total resistance. 12 volts divided by 218 ohms gives me 0.0550 amps. Now again, I use the 0 at the end for significant digits. Okay, now that I have it solved at this point, I know the total current, I know the total resistance, I know the total voltage. Now I can start putting the circuit back together again and solving for any of the unknowns as we go. So going back to diagram 3, we know that the current is going to be split up into 2 parts. The voltage drop across those 2 paths is going to be exactly the same. But now I want to find the current in each of those branches. So again, we're going to use Ohm's law. And we find that I1 is going to be equal to V1 divided by R1. So in this case, it's 12 volts divided by 360 ohms, which is going to give us 0.0333 amps. For the other side, we're going to have I2 is equal to V2 divided by REQ1. And in this case, it's 12 volts again, divided by the 555 ohms. And we're going to find that that equals 0.0216 amps. Now, a good check here. Remember that we said that the total current was breaking off into 2 parts and it was going to come back to a total current. So we should find that the sum of I1 plus I2 should equal the total current. And if we put this together, we have 0.0333 amps plus 0.0216, we get 0.0549. Now, what did we say the total current was? 0.0550. So we're off by a very small amount. Well, why? Well, again, go back up and look. We said the actual equivalent resistance was 218.4 ohms, and we rounded it to 218. That's where it is. Okay, now we're going to go back and we're go up to one more step back. We now have the 2 resistors in series across from the one in parallel. And this time we want to look at the voltage drop. Now, we know that through the parallel circuit, or the parallel portion of the circuit, the voltage drop is still 12 volts, which means that the voltage drop across each of those lines is 12 volts. But what is the voltage drop now across each of the resistors? Now, finding the voltage drop across the R1 is very easy. It's 12 volts. But what about R2 and R3? For that, we have to go back to Ohm's law. We're going to use V2 is equal to I2 times R2, 0.0216 amps times 430 ohms equals 9.29 volts. Now to find V3, remember it's the same current that's going through that line, I2. So we're going to use I2 times R3. So again, 0.0216 amps times 125 ohms for a total of 2.70 volts. Now again, we should be able to check this. We know that the voltage drop across that line has to be 12 volts. We have the 2 individuals. They should add up to 12 volts. Let's see how they do. 9.29 plus 2.70 is 11.99. Now we use 3 significant figures everywhere. That's going to go to 12.0 volts. So where else besides Christmas lights do you think you'd find a combined circuit? Do me a favor, leave a comment in the area below and tell me where you think you might find some. Now, the only way you're going to get better at working with combined circuits is to practice them and practice them regularly. Now, right now, you have the very basics on how to solve them. What I suggest is start off slowly. Take the example we used, try it on your own. Can you do it? Then change some of the numbers, change the resistance values, change the battery, and figure out if you can still do it. And then start adding pieces on, increase the difficulty level. It's always the same series of steps, in and out. If you haven't picked up your free copy of my PDF, the 15 Tips to Improve Your Science Grade, I've got a link for that in the description for the video below. If you like this video, please let me know by liking it, subscribe to the channel, and please share it with somebody else that you think is going to benefit from it. Well, that's all for this week. I'm Robin DeMarco, the online physics teacher. Thanks for watching, and I'll see you on the next episode.